When we have a sequence of real numbers, we can always think about the convergence of the sequence as obviously n goes to infinity. Now, exactly in a similar fashion, if we have a sequence of random variables, as we have seen that there are some examples where, or there are some theorems which deal with sequence of distribution functions, sequence of characteristic functions and so on. So, suppose we have a sequence of random variables. Now, when we have a sequence of random variables, then the convergence can be thought of in different ways. As for example, for a sequence of random variables, we can have a sequence of distribution functions. We can have a probability event, and for each random variable we can consider a sequence of such events or sequence, and then calculate the probability. We can also think of the expectations of the sequence of random variables. So, for each of these situations, we have to define what is the meaning of convergence, and naturally since expectation and the distribution functions, they are really of some different nature. So, we have to define the convergence with respect to each of them separately. So, today we will be defining some different modes of convergence corresponding to random variables, corresponding to distribution functions or some of the characteristics, and we will discuss some results relating to them, whether there is any interrelations between them and so on. Let us first define a few types of convergence relating to a sequence of random variables. The first one is convergence in distribution. So, the definition goes like this: a sequence x n of random variables converges to a random variable x in distribution if f n x, that is the sequence of distribution functions corresponding to the sequence of random variables, this converges to capital F, that is capital F x, that is the distribution function of the random variable x at every point x, which is a continuity point of f, where f n and f is defined, I have just mentioned. So, this convergence is basically with respect to the convergence of the sequence of distribution functions. That means, we are interested to know whether a sequence of distribution functions converges to another distribution function, that means for which we can define a random variable. Now, one important point we should note that it is enough to consider this convergence only at the continuity points of the final distribution or the limiting distribution function. We usually write that x n converges to x weakly, that is why the W, or x n converges to x in distribution, that is D, or x n converges to x in log. Another type of convergence that comes immediately, which is called convergence in probability. So, a sequence x n of random variables converges in probability to a random variable x if probability of this event, probability of the event that modulus of x n minus x greater than epsilon, this probability should be very small, that is goes to 0 as n goes to infinity for every epsilon greater than 0. Obviously, epsilon should be taken to be very small. Now, that means, as n goes to infinity, there is basically no difference between the probability of the outcomes of these two random variables, that is x n and x. So, we write x n converges to x in probability, that is p. Now, this theorem states whether there exists any relationship between this convergence in probability and convergence in distribution. So, one such, the first theorem in this direction is x n converges to x in probability, that will always imply that x n converges to x in distribution. So, naturally the question will arise that whether the reverse is true. That means, is it true that when x n converges to x in distribution, does this necessarily imply that x n converges to x in p? Answer is not really yes, but there is some situation, there are some situations where we can get this, where the answer would be yes. That means, the one situation is if x is a constant, that means x is a degenerate random variable, that means probability x equals to c is equals to 1, then this convergence in distribution, that is that means x n converges to c in distribution will always imply that x n converges to c in probability. So, let us consider the proof, at least brief outline of the proof. We start with the concept of with the given condition of convergence in probability, that means probability mod x n minus x less greater than equals to epsilon goes to 0 as n goes to infinity for every epsilon greater than 0. Now, consider one x which is a continuity point of f, that means which belongs to the set of continuity points of f. Then we are interested to see whether the sequence of distribution functions corresponding to x n converges to a distribution function of a random variable. So, naturally we start with the distribution function corresponding to x n, and that means we start with probability x n less than equals to small x. This is nothing, actually this is nothing but f n x. Now, suppose this is the event A and we introduce another event B. So, we can write probability of A equals to probability of A intersection B plus probability of A intersection B complement. So, suppose our event B is defined as x capital X less than equals to x plus epsilon. So, naturally B complement will be x greater than x plus epsilon. So, we can get immediately probability x n less than equals to x equals to probability x n less than equals to small x comma capital X less than equals to x plus epsilon, that is intersection of these two events, plus probability x n less than equals to small x comma x greater than x plus epsilon, which is the B complement I have mentioned. So, from here just a little bit of manipulation and noting the fact that we can always write this event probability x n less than equals to x comma x less than equals to x plus epsilon is less than equals to probability x less than equals to x plus epsilon, because we know that A intersection B is a subset of B, and hence probability of A intersection B is less than equals to probability of B. So, from here we can immediately get probability x n less than equals to x minus probability capital X less than equals to x plus epsilon, which is less than equals to probability mod of x n minus x greater than epsilon. This event comes from the previous line, that is from the event probability x n less than equals to x comma x greater than x plus epsilon. Now, the last term, that is probability mod x n minus x greater than epsilon, this goes to 0, because we know that the given condition says that x n converges in probability to x. So, this goes to 0 as n goes to infinity. Now, if we take the lim sup over n, then lim sup of f n x minus f of x plus epsilon. Naturally, f of x plus epsilon has no n involved in this expression. So, this less than equals to 0 implies lim sup of f n less than equals to f of x plus epsilon. Now, proceeding exactly similarly, as n goes to infinity, we can again get probability x less than equals to small x minus epsilon minus probability capital X n less than equals to small x. This actually gives us the f n x less than equals to, again we get probability mod x n minus x greater than epsilon, which goes to 0. Now, if we take the lim inf on both sides and noting the fact that probability x less than equals to x plus x minus epsilon is basically independent of n, we can immediately say that lim inf of f n x greater than equals to f of x minus epsilon. Now, two important things that we should note: we have taken x as the continuity point of f and epsilon is arbitrary. So, limit of epsilon goes to 0, limit of f of x minus epsilon is exactly equals to limit epsilon goes to 0 f of x plus epsilon, which is nothing but f x, because x is a continuity point of f. So, using these facts, we can immediately get that lim sup of f n x less than equals to f x less than equals to lim inf of f n x. But one thing is always true, that lim inf of anything, any sequence is less than equals to lim sup. That means lim inf of f n x less than equals to lim sup of f n x. This is always true. So, combining these two, we can immediately get probability that limit n goes to infinity of f n x equals to f x. Now, for obviously x is a continuity point of f. So, this is basically the definition of convergence in distribution. So, we can immediately say that this will imply x n converges to x in distribution. So, now this proof is complete. This says that whenever we have a sequence of random variables and we find that this sequence converges to some random variable in probability, we can immediately have we can immediately say that this same sequence converges to the same random variable in distribution also. Now, let us consider the proof of the B part, that means the other way around, or rather when we can see the reverse situation might happen. And we have mentioned that when capital X is a degenerate random variable or a constant C almost surely, then convergence in distribution implies convergence in probability. Now, without loss of generality, let us assume that x of omega equals to C for all omega, because x is a degenerate random variable. So, probability x equals to C equals to 1. So, whenever we observe any observation which is less than C, probability of observing that observation is 0, and whenever we reach or x takes a value C, the probability is 1. So, naturally it is clear that capital F x, the distribution function corresponding to this random variable, can be written as 0 less if x less than C and 1 if x greater than equals to C. So, it is clear C is the only point of discontinuity of capital F x, because if we define x over the entire real line, C is the only point of discontinuity. Just let us consider whether convergence in probability holds good for this sequence of random variables. So, and we know that this x n converges to x in distribution, that is given. So, if we want to calculate this probability, that probability mod of x n minus x greater than equals to epsilon, if we can show that this goes to 0 as n goes to infinity, then the proof is complete. So, this thing equals to, since capital X equals to C with probability 1, we can replace capital X by C and get probability mod of x n minus C greater than equals to epsilon, which is equals to probability x n greater than equals to C plus epsilon plus probability x n less than equals to C minus epsilon. Now, this probability x n greater than equals to C plus epsilon is nothing but 1 minus f n C plus epsilon minus, and that means this is 1 minus probability x n less than C plus epsilon, and probability x n less than equals to C minus epsilon is f n of C minus epsilon. Naturally, this tends to f of C minus epsilon minus, because f n converges to f and again f n converges to f. So, f n C minus epsilon converges to f of C minus epsilon, and it is clear that all C plus epsilon, C minus epsilon, they are all continuity points of f, because f has only one point of discontinuity, which is C. So, if we calculate this thing, probably that capital F of C plus epsilon minus is 1 and f of C minus epsilon, that means it is less than C, is 0. So, the probability of mod x n minus x greater than equals to epsilon goes to 0 as n tends to infinity. So, this implies that the convergence in probability is now proved, given when convergence in distribution to a degenerate random variable. Let us consider one small example of a convergence in distribution, which is called CLT. Suppose x n is a sequence of random variables with expectation of x n equals to 0 and expectation of x n squared is finite. Then if we consider the sum of random variables, that is S n equals to x 1 plus x 2 plus x n, then S n by sigma root n convergence in distribution to a standard normal variable. The proof actually is followed using characteristic function. So, just calculate the characteristic function of this variable S n by sigma into root n, which is expectation of e to the power I t S n by sigma root n. Just little bit of manipulation will give us, this is phi of t by sigma root n whole to the power n, phi being the characteristic function of x I. Then this is equals to, we can write this as an expansion in t, which is 1 minus sigma square t square by 2 n sigma square, plus rest of the terms we can consider, we can just neglect it, these are negligible, whole to the power n, and this sigma square cancels, and this converges to e to the power minus t square by 2 as n goes to infinity. Now, we know that e to the power minus t square by 2 is a characteristic function of a normal 0 1 variable, and hence by inversion theorem, we can say that this is the characteristic function of a normal 0 1 variable, and naturally using continuity theorem of characteristic function, we can say that this converges, this sequence of random, this sum S n by sigma root n converges to a standard normal variable in distribution. This follows directly from the continuity theorem of characteristic function. Another example is this is for convergence in probability. This is known as Khinchin's weak law of large numbers. It says that a sequence of IID random variables with common distribution function f x and finite mean n, then S n by n, S n is sum of n random variables, IID random variables x 1 plus x 2 plus x n, this converges to mu in probability. Again, just calculate the characteristic function, and we know that characteristic function for a random variable phi t can be written as 1 plus I t mu plus small o of small o of t, that means this part goes to 0 as t goes to 0. Then if we calculate the characteristic function of S n by n, that is expectation of e to the power I t S n by n, which is nothing but product, since these are IID random variables, product of e to the power I t x j by n, product over j equals to 1 to n, which is phi of t by n whole to the power n, and if we simplify this 1 plus I t mu by n whole to the power n, this goes to e to the power I t mu. Now, e to the power I t mu is the characteristic function of a degenerate random variable x at x equals to mu, almost surely. So, naturally again by continuity theorem of probability, we can immediately say, we can first say that S n by n converges in distribution to mu. Remember, this is continuity theorem says the convergence in distribution, and the theorem that just now we have proved that convergence in distribution to a degenerate random variable implies convergence in probability. So, from there we can immediately say that S n by n converges to mu in probability. Another simple result, that if there are two sequences of random variables, one is x n goes to x in probability and y n goes to y in probability, then x n plus y n will also converge to x plus y in probability, and x n into y n converges to x and y, x into y in probability. So, the first proof of the first one A is very easy. Just calculate the probability mod of x n plus y n minus x plus y greater than equals to epsilon, which is less than equals to probability mod of x n minus x greater than equals to epsilon by 2 plus probability mod y n minus y greater than equals to epsilon by 2. And this will imply that since both x n and y n converges in probability to 0, so the two terms on the right hand side goes to 0 as n goes to infinity, and hence we can immediately say that probability mod of x n plus y n minus x plus y greater than equals to epsilon goes to 0 as n goes to infinity, and hence the proof. Similarly, we can prove the B part using the same kind of argument. Let us now define another type of convergence which is known as convergence in Pietvin or LP convergence. So, if expectation of mod x n minus x whole to the power t goes to 0 as n goes to infinity, we say that x n converges to x in Pietvin or in LP, and we write x n converges to x in LP. One small theorem is that x n goes to x in LP implies x n converges to x in probability, and I just give you one proof of Markov-Chebyshev's inequality which is known to almost all of us. So, it says that for a non-negative random variable such that expectation of x to the power p exists for p greater than 0, then probability x greater than equals to epsilon less than equals to 1 by epsilon to the power p into expectation of x to the power p. So, we start from expectation of x to the power p, and which is greater than equals to integration not over the full range, but over the partial range, that is x greater than equals to epsilon x p x to the power p d f x, which is naturally greater than equals to epsilon to the power p into probability x greater than equals to epsilon, and hence the proof of Markov inequality. And proof of theorem 3, this theorem is just a direct consequence of Markov-Chebyshev inequality, which says that we want to prove that probability mod of x n minus x greater than equals to epsilon should go to 0, and which is less than equals to 1 by epsilon to the power p into expectation of x mod of x n minus x to the power p. Since x n converges to x in LP, so expectation of mod of x n minus x to the power p goes to 0, and hence the proof. So, convergence in LP always implies convergence in probability. And just one small definition, that is converges almost surely. So, a sequence f n of extended real valued function is said to be converge almost everywhere or almost surely on a measurable space x b mu or a probability space omega script b and p to a limit function f if there exists a set E belongs to B with mu e equals to 0, that means with probability of E equals to 0, because probability is also a measure. So, if you take mu equals to P, we can get probability of E equals to 0, and if x belongs to E complement, that is where mu e or probability of E not equals to 0 or greater than 0, then and epsilon greater than 0, we can always have f n x less than 1 minus 1 by epsilon if f x equals to minus infinity, if mod of f n x minus f x less than epsilon if mod of f x less than infinity, and f n x greater than 1 by epsilon if f x equals to infinity, whenever n greater than n naught, that might depend on x and epsilon. So, another definition, a sequence f n of measurable functions is said to converge to f in measure if given epsilon greater than 0, there exists a positive integer capital N such that for all small n greater than equals to capital N, we have mu of the event x such that mod of f n x minus f x greater than equals to epsilon must be less than epsilon. That means, it is very close to 0, and we write that f n converges to f in mu. Now, if we take mu as a probability measure, f n as a sequence of random variables, which is a measurable function, f is another limiting random variable, that is x, then from here we can immediately write x n converges to x in P. So, actually convergence in probability can be thought of as a general can be generalized to a similar concept of convergence in measure. And one theorem, I will just state this theorem without proof, that convergence almost surely implies convergence in measure. That means, for a random sequence of random variables, if we know that this x n converges to x almost surely, then x n converges to x in probability. So, this is since probability measure is finite. So, here the condition is mu, the measure is finite, probability measure is naturally finite. So, convergence in almost surely implies convergence in probability. So, today we have studied different types of convergences. We have seen that convergence in probability, convergence in distributions, convergence in pth mean or LP convergence, converges almost everywhere, etc. Now, we have also seen some results relating to convergence in probability and convergence in distribution, some examples of which are known as Khinchin's weak law of large numbers. We have also studied this LP convergence and how it is related to the convergence in probability, convergence in probability. So, we have some clear idea about different types of convergence, and it is clear that there might exist some relationship between these different types of different modes of convergence. We will discuss something more on these interrelations among these different types of convergences, that means whether one implies the other or the other way around, and so on. So, that will be taught in the next few classes.